the mean time to failure is a very useful and popular measure of reliability, especially for electronic components, machine parts, and not so much for structural members, for building systems and so on, mainly because in structural engineering the failure probabilities are so rare that it's not so much practical to talk about the mean time to failure of a building or a bridge. But let's define it. The MTTF, the mean time to failure, is the expectation of random time to failure t, and because we define t only for non-negative values, 0 up to positive infinity, so that's what you see on the limits of the integration. But that also gives rise to, which we'll prove next, to the last equation on the right, which says that the mean time to failure of a component is the area under its reliability curve, and which is actually a very useful property to have in some situations, such as when in a test program not all the members that we start with, not all the specimens that we start with fail before the test program is over. So there are many specimens which last longer than the duration of the test. So if we estimate the mean time to failure as just the average of the observed times to failure, then obviously that would be an underestimate of the actual mean. So in such cases, it's much better to estimate the reliability function and extrapolate it beyond the time of the test program, and then estimate the area under it. So that would give a closer value of the MTTF. Now let's see if we can prove how the last equation comes, that the MTTF is the area under R of t. By definition, MTTF is, as you see there, the integration of TFT over the entire range. Now, by definition, f of t, the density function of t, and the reliability function of t are related, that the density function is the negative of the derivative of the reliability function. Why? Because the reliability function is 1 minus the CDF, and the density function is the derivative of the CDF. So the density function is the negative of the derivative of the reliability function. So that's how you see MTTF is also negative of t dRt when the limits on t is 0 to infinity. Now we can expand this by integration by parts, and so the first one is TR evaluated at 0 and infinity, and the second one is the area under the reliability curve from 0 to infinity. So the first term we've evaluated at infinity, so TRT when t approaches infinity, and the other one is TRT evaluated at 0, which obviously is 0 times 1, because at t equals 0, r starts at the value 1. So, but what happens to the first term, the limit of TRT as t goes to infinity? It so happens, and which we will clearly see when we define the hazard function, is r of t goes down faster than t. So t times rt as t goes to infinity approaches 0. So that first term ends up being 0. So we are left with the area under the reliability curve that we showed at the beginning. A related measure coming out of the random time to failure is the mean residual life. So we now expand the definition of the mean time to failure as a conditional. So it is the mean time to failure given that the structure, the system, the item has survived up to the present instant. So capital T greater than little t. Based on that event, conditioned on that event, I want to find the mean. So it's a conditional mean that we are looking at, and we have defined and we have worked with conditional means before when we were discussing joint distributions and etc. So this by definition we can show in a minute, we'll prove it, but this ends up being the area under the reliability curve from t onward and normalized by the reliability at t. So let's see if we can prove it. So this is our starting point. The definition is that the mean residual life at small t is the expected value of the remaining life, so capital T minus small t, on the condition that the capital T is greater than small t. So we use the definition of a conditional probability that E of A given B, so we express that as the ratio. In the denominator you have the probability that capital T is greater than small t, which by definition is the reliability at small t. So we have figured out that part, and now let's focus on the numerator. The numerator would be the integration from t to infinity of tau minus t times ft dt. Let's expand that. We can go through the algebra, and it comes out looking something similar, which we have already seen in the case of the MTTF, is we have within the brackets the area under the reliability curve going from t to infinity, and then the limit of tau r tau as tau goes to infinity, and then TRT added and subtracted. So they cancel out each other, and what we are left with is, by the same logic, limit of tau r tau as tau goes to infinity, it vanishes because r tau falls off faster than 1 over tau, and then we are left with the expression that we started with, and the mean residual life is the area under the reliability curve starting at t, so to the right of t, and normalized by the reliability at that instant. Just as a check, when t is equal to 0, we are left with just the mean time to failure as it should be.